So, my name is Matan Breizman, and I've been working on Crimson on the past year or so, a little less than 2 years for now. And today I will be presenting my talk named From Classical to the Future. So, let's start. For those of you who have been to Sam's Crimson status update yesterday, this slide is already familiar, but it's essential to understand why we do what we do with Crimson. So there have been some, everyone here is aware, recent technological changes in terms of speed of storage devices. So we know that HDDs and so-called spinners can draw around 75 or 150 IOPS for 4K reads. However, NVMEs can draw a much larger number than even the ones we see here. It's only 500,000 IOPS. So let's continue. So this slide is represent the same data we've seen in the previous slide, but from a different perspective. In this slide, this is for a single CPU core with, let's say, a clock speed of 3 gigahertz, which is 3 billion cycles per second. The budget, meaning the number of IOPS we can allow ourselves to spend before reaching a CPU overhead. For HDDs, it's a quite far large number, 20 million cycles for a single I/O. But for NVMEs, the story is different, and we can allow ourselves to spend much less, around 6K cycles for a single I/O. So what we really want to do is to drive down our CPU overhead in order for us to exploit these new faster storage devices. So CPU isn't moving the same way as storage devices does. This is a quite famous slide, and this slide actually represents the last few decades in terms of microprocessor trend data. So one of the most distinct trends here is the orange trend, the upper one, the orange one, which represents what it's named Moore's law. Moore's law is an observation that says that the number of transistors on a microchips will double itself around every 2 years or so, and we can see this is in fact the case in the orange trend, the upper one. Now, what Moore's law has given us is also a large increase in the single thread performance, the blue trend right beneath it. But this trend has reached some kind of plateau around 2008 or 2010. We can see that it's stopped doubling as it did before. However, what we gain instead is an increasement in the black trend, the core count, the logical core count in CPU. We've scaled from a single core up to, we started doubling instead up until today. So what we have is an increase in logical cores, but not an increase in per core throughput. So our key metric here that we will talk today is I/O per core, rather IOPS as a whole, because we know that Ceph can draw today a rather large number of IOPS. But Ceph, if I can say, is quite heavy in terms of software architecture on CPU usage. So we really want to make better use of our large core count. So this is a funny picture. I think will sum up my next point. We've seen that machine from over 1 decade ago, from 10 years ago, is really different from machines we have today. And one of the most distinct changes is the number of logical cores. So in theory, large core count should reward certain programming practices as we want to in theory. But in practice, it can also decrease our performance. In practice, as we see in the right side, the story is different because unscalable programming practices, such as taking locks and so on, really reduce our performance on large core count. So, however, we have shared memory and lock-free synchronization primitive. They are available like atomic operation, but they are much slower. Needless to say, they are much slower than working on a single core cache. So what we really want to behave is how we have our theory. So this is why we come up with Crimson. In Crimson, our goal essentially is to minimize the CPU overhead per I/O by avoiding context switches and by avoiding cross-core communication in order for us to exploit fast storage devices we have today. So how are we about to do that? Essentially, Crimson is a rewrite of our current OSD, of our current I/O path, efficient rewrite using the Seastar Framework, which I will talk a bit more thoroughly than what we do usually today. We will remember that one of the key concepts is the single thread per core and the explicit sharding over cores, meaning each data structure and each request is sharded onto individual cores. So we have no need for locks. And by having no need for locks and by skipping or avoiding the expensive context switch we have on threaded model, we really largely reduce our memory traffic. So Seastar Framework is an open source, of course, CPP framework for asynchronous programming for modern hardware. Now, the key concept that we are looking for that help us with our goal with Crimson, particularly in Seastar, and why we use that, is because of three main reasons. The first is the shared nothing design. Shared nothing design says, as I said earlier, each request is sharded into individual core. And the second one is the future and promises. Now, future and promises is a programming model, concurrent programming model, which I also will be talking about a little more deeply now to understand the difference in behavior in terms of code and even general behavior. And the last one is the message passing. Seastar also offers a message passing design that allows us to essentially share messages between cores without really having to lock them. So let's talk about future and promises. Future and promises are the building blocks of asynchronous programming. A future is a result of a computation that is taking place that may or may not be available yet for us to use. Now, example for futures, future representation are a completion of a disk write, which is taking place, which is really relevant to us. Expiration of a timer, a data buffer that we are reading from network or from disk, and also a result of a computation that requires values from other future we are currently waiting for. So, what is future? Future essentially has three states. A future has an unavailable state, the first one. An unavailable state means that currently the computation is taking place and we cannot use its value. It's not available yet. However, the value one, the second one, or available, the value or is ready for us to use. The computation is over. We finished with our I/O, let's say, and we can use this value now to continue with our logic, with our behavior. And the last one is fail. Now, if we had any exceptions, let's say in our computation, while we try to compute or perform the I/O, and we had any exception we want to handle, same as we have CPP catch throw expression, so we have a failed state for this future for us to handle accordingly. Small few thing about future states is that methods that use future can query for the future state. So it's really important to know what is the future state right now. And most importantly, they can schedule a continuation on top of this future to be executed once the future is resolved. And we have only single continuation for a single future, and the future will never be discarded. We must always extract and use its value. So the second half, and I will use a real-life analogy to make it the relationship quite clearer. So a promise, the second half of future and promises. A promise is the object that essentially allows the future to be resolved by assigning it a value. A promise is the provider of the future result, as the slide says. Now, we can remember future and promises as reader and writer side. We read from the future, but we write to the promise. So, I think I will show it with a burger restaurant analogy because this will play out really well to explain the relationship between those two. So we will remember that the consumer side is the future side and the promise is the producing side. So in the analogy of me while I order a burger from a restaurant, from a burger joint, so the receipt, when I pay for my order, the restaurant promises to deliver me a future burger once it will be ready. And while I wait, while I wait for my meal to be cooked, I can do other stuff like grabbing a soda and so on. So let's see it in the timeline here. I will explain and go over it. So we have the consumer, and we have a request from the producer to have some food in the right side. Now, immediately, the producer will create a promise and return me a future representing this food to come. And now, I have a future in hand. I'm not blocked to do other stuff, like grabbing a soda, in this case. And meantime, my food is being cooked. And while it's being cooked, when it's finished, the producer side will fulfill the promise by actually writing to the promise the food that I waited for, or setting the future value to ready. Now I get notified that my future has available value within it. I can use it and drive safely home. So we've seen future, we've seen promises. Now it's time to actually make use of them. How we usually make use of future and promises is by chaining continuation on top of them, as I said earlier. Now, a continuation is usually a block of code for the CPP developer. Here it's a lambda expression, most usually, that is called when the future will be assigned a value. Essentially, a continuation is a definition of a task that will be executed upon the completion of some other task. And of course, the continuation can access the future data to actually make use of it. So back to Ceph, enough with the programming model. In Ceph, in the upper side, we see the classic code, the most simple synchronous code for our stripped down version of our messenger in Ceph. We have three basic calls of receiving a request in a for loop. We read the request, we handle the request, and we send the response back. Now these are three blocking calls, and in Crimson, we have the same code, but now it's translated into Seastar continuation, which makes the code appear much more differently. So this is essentially our talk today. I will show how the code is being rewritten in a user-friendly, of course, simplified version, and how we handle, in this case of this presentation, how we handle the metadata of objects when receiving requests from clients into Seastar. In slang, we call it, in Crimson, Seastarizing a component. So we'll translate it from classical code, the OSD, as we refer to him as the classic one, to future. Hence the name of the presentation, from classical to the future. So now I'll go over a really basic Ceph OSD operation message. So in Ceph, we have the messenger component. Now, the messenger component is basically our communication layer. Messenger is what allows us to pass messages between components, between daemons in Ceph. We have various types of messages. We have a message of ping, of getting pull stats, and so on. One of the most notable messages is the OSD operation message, or the MOSD op in short. This message is a RADOS layer operation that basically where all the fun and action happens in terms of read the writes to our objects. Essentially, it's a message that is getting sent from an IO request that is getting sent from client to our OSD. So it will really make interest to us in the following slide. Now, this message basically contains the object ID and a series or a vector of ops like write, delete, so on, etc. So let's go over the basic case. We have the client makes a request by sending a MOSD op message to our OSD. Now the OSD will handle that accordingly with the doOp function. The doOp will later on send a reply back to the client with the reply about whether the operation is successful or not. So what is the doOp function? So we see we have here doRequest. A doRequest function gets the op message as a parameter, and according to a switch case, which will in different types of messages, in our case is the Ceph message OSD op, will go straight to doOp to handle this operation. In the box here we see. So what is doOp? A doOp, most simplicity, consisted of three stages. The first stage is the error checking phase, where we check for basic error, whether the operation is allowed, whether it's sent to the right OSD, whether the client is not blocklisted, and so on. After we checked for this, for the errors, and we can continue, we find the object context. The object context will be responsible for our metadata. We will see it soon. And when we have it in hand, we can execute the operation and start actually handling and executing this operation. So again, the source code of DoOp, of course, it's a simplified version, but it will help us to see the difference in terms of asynchronous programming. So we have the DoOp function. The DoOp function, as I said, is constructed of 3 layers, of 3 stages. The first one is the error checking phase. It's a really simple check for errors. We check if the object name is empty. If so, we reply with an error. Of course, there are much more checking, but I wanted them to fit into one slide. The second stage is we initiate the object context class, data type, and we find it. And I will explain short how we find it actually. When we have it in hand, this is the third box, we go ahead and execute the operation. So simple 3 steps. So what is the object context? Object context is a cached data structure that help us to keep track of data modification that are in flight, meaning it helps us to have a projected metadata after all operation will be complete without actually needed to wait for them. So in example, if we have a write request that we are now performing, and then a read request, let's say, and then a write request comes along to the same object, this write request will hit the same object context and will hit the same object context locks and will know to block the read request to the write request until the read is finished, or vice versa, depending on our case. So this is a basic UML representation of the object context class, just to have better understanding what it has inside. So I'll go over its members. It has the SSC, which stands for snapset context. Snapset context help us to have the relevant metadata of snapshot and clone object and so forth. Second, we have the watchers map, which basically allows us to allow a client to register a persistent interest in a specific object to be used as a watch notify communication channel. And then we have the object state, which has all the object information, name, ID, time created, and so on. And lastly, the read or write state, the RW state, which has 2 integers, the count and waiter. The counter of all the existing operation and the waiters, the read or write waiting operation, to know how to handle those. So how we get it? How we get the object context? Really simply, I would say, in this graph. If the object context is cached, we ask whether it's cached or not. If it's cached, we just get it from cache and return it to our logic to continue. If not, we load it from disk. Now this path will require essentially an I/O. So let's remember this path here. And in the end, we update the cache and return the object context. So again, we will see it in code here, in a simplified code. So we have the get object context, which gets the object ID as a parameter. And in the first box, we try to look up for it in cache. If we find it, we do nothing. If not, we create it, or we load it from disk in our case, and we return it. So let's sum up a basic OSD operation. So an MOSD op message gets sent from client to the OSD. Now we need to handle this operation. So we have the 3 basic steps: error checking, loading or creating the object context, and executing the operation. So again, I'll show this slide for us to remember I want us to remember the same 1, 2, 3 stages: error checking, finding object context, and executing the operation. Because now comes the part when we actually compare it to Crimson behavior. So I will start by classic. We have 1 and 2. The 1 is checking for error, 2 is finding the object context. Now let's say we don't have the object context in hand. We need to send a request to the disk for us to find the existing object context in disk. So we make a request, an I request to the disk. Now in this time, we will have a kernel space context switch, which will be scheduled, of course, by our operation system. Now this context switch is quite expensive and slow in terms of mostly depends of the size of our block thread stack. Now, after all, of course, after the I/O is finished and the context switch is back to our case, we will execute the operation. However, in Crimson case, the green one in the right side of the slide, the same 1 and 2 option, again, this is the same logic, we are not inventing anything new. This is the same 1 and 2 stages, but now the request is getting sent to the disk, but instead of having the context switch, we immediately get returned by a future. So we immediately are not blocked to perform other work in the same core, in the same thread. This is more of a task switch which is scheduled by Seastar Framework, essentially, and not by operation system. And this is how we want us to handle I/Os. And of course, when the I/O is finished and the future has an available value, it has the I/O computation is over, we can go ahead and execute the last step. So let's compare between a task switch, as I said, in the user space task switch, between a kernel space context switch. Why we prefer that? Because when we have a task switch, so-called, the future, if the future is not available, its continuation state still will need to be copied, and we will need to allocate memory for it to be used later. This is still an overhead. This is an overhead, but it's unavoidable and it's really small, meaning we cannot actually compare it to a context switch, an expensive context switch that happens, as I said, in the operation system, in the kernel space, which is much more slower. So how does it happen? How do we rewrite this code? So we've seen a similar slide. We have the client which sends in a request to the OSD, but now it's not the classic OSD anymore. It's the Crimson OSD which handle it and will send the response back. Now, we will notice that it's the same message, exactly the same message which will be sent and will be responded, meaning the client will not be aware of any changes underneath, whether it's a Crimson OSD or classic OSD. So, but now the difference is that Crimson OSD will handle the operation with a function we have implemented named process operation. So now we see this code is slightly different than what we've seen earlier. This is the Crimson way of writing this, how we handle the message. So I will go over it. I will try to make it as simple as possible. So we have the future return value type from our process op function. And we have 3 boxes. The first one is we have the object context loader component in Crimson that has a method named with OBC that allows us to load object context, same as we did in Classic. And once we will load it, we will use it with the do process function with this loaded object context. And if we had any errors while trying to load the object context, we reply with an error back to the client, same error code that we will do in Classic. So how with OBC is looking? So we have 2 parameters, the object ID and a callback function. We've seen earlier it's the do process that will be called once the future which hold the object context will be ready to use. So we have get or load that receives the object ID and it will return us the loaded OBC. Now, once the loaded OBC is a future which has object context within it will be available, will have value inside, we will apply it onto our callback function, which we've seen earlier. It's the do process function. So this is the last, I would say, new function we see today. So don't worry if you've seen too much code today. This is now the get or load OBC with an object ID as a parameter, as we've seen. But now the carried data type within the future is in the type of object context. So it's not just a timing future. We actually has a value we want to use inside of it. So the logic is quite the same. We go to our cache and we search for the object context. If we have it, good. We found it in cache. We will return a make ready future. A make ready future, we will create a future in an already resolved state, meaning we don't need to perform any additional I/O. We can straight up use our object context we got up from our cache. And in the other case, the second case, we load it from disk. We actually have the load OBC function, which will return an unresolved future in hand that due process will need to wait before it can actually use it. So this is the with OBC again, just because we've seen get or load. So let's see with OBC again, now that we know how it looks like. So we have the get or load, and it will return us the loaded OBC in the second line here. And once it's ready, this is a Seastar continuation. Once it's ready, we apply the function into, we pass the loaded object context into our callback function. So life is not really that simple, as we've seen in the slides earlier. This is like more like a chunk of the due process code we have in real life. There are much more things to which, of course, needed to be taken into account, and it won't fit in a single slide. And getting used to asynchronous programming in C++ with a new framework can be quite tricky in first, and we can see we can get to a situation where code is really complicated. However, after some time, getting used to this programming model, you can really see the simplicity. I wouldn't say simplicity, but you see why we use it, and it makes it much easier to continue developing using it. So this slide wasn't supposed to scare you, and of course, any of you that wants to join Crimson and want to help us make the OSD quite faster for faster storage devices is welcome to join us or ping me or anything. Thank you very much. I was Matan. I hope you enjoyed. I'm not sure about the timing, but I think we do have time for questions. So if anyone wants to, we can try to give it a hand. I don't see any handed.
How much faster is code when I convert it to Crimson?
So that's a good question, and it's a tricky one. Basically, in the first place, we want to get to a position where we actually have I would call it minimum viable product, something an OSD that works first, asynchronously. Because in the first place, we just implemented it with a single core and not a multi-core version. So when we had performance testing in the first place, which Mark did, which you can see in the Ceph blog, is different from performance we will have that will have multi-core support that we have right now, and also multi-reactor support. So the performance, I agree with you, that is really important here, and this is actually the stage we are into right now, now that we have a basic version. It's rather basic, but we have features that we didn't have earlier in terms of RBD support, of snapshot and workload, and bugs we had to solve before reaching that point that we didn't have earlier. So now, I would say it's time to focus about performance, and this is actually what we're performing now. So we introduced the performance testing suite not a while ago, and this is so. The next presentation I will give will be probably with a more performance terms data. Yeah. Oh. Let's
questions.
What?
The microphone for questions.
Oh, okay. Sam, you wanna?
Yeah, one of the performance.
I'll give you a mic.
So there was a modest performance benefit, like a double-digit %. The bigger benefit, however, was tail latency, because you don't have the scheduling non-determinism portion. So that's the main thing we're going for here.
Any more? Can you give him, please?
Yeah. How much refactoring have you done to provide this future and promises?
So it's not a refactor. So a refactor, in terms of a refactor, is rewriting our already existing classical code. So what we do here is not essentially a refactor. It's a new OSD. It's a new code, definitely new code from scratch. Of course, we had to actually refactor some classical components to make them to not rewrite all of our OSD daemons and so forth. So the Crimson OSD is, I can say, from scratch. It's the same logic, but we need to actually rewrite it with the Seastar Framework. And today, of course, you can see in GitHub, but we've got to a point that we actually support we support a full Rados API test, and we have a basic RBD load test that are supported today and can be already used for minor testing.
I mean, from a high level, the Seastar framework looks like the C++20 coroutine approach.
Right. So
What's the difference?
So, see, the coroutine will help us. It will cooperate with our Seastar re-implementation, and I think I talked about this with Sam not a while ago. So I'll give it.
Yeah, so the standard library, coroutines library, if anyone's looked at it, is less a coroutines library and more a toolkit to build one, right? So the Seastar developers fortunately did this for us already. They added hook-ins that wire the standard coroutine primitives up into Seastar's threading library. So I actually added machinery for it. So code going forward, we're probably going to start using the coroutine stuff directly. But you can mix and match. You can call stuff that uses perfectly conventional futures from coroutines and vice versa. The Seastar threading machinery doesn't care.
Let him go now. Okay. Oh, so you'll be after.
How to debug the future promise still the code?
It's a good question. It's a really good question. It's also quite tricky, I would say, because it's much less convenient to debug when you have a future wait for it. This is a really good question because we have our tricks, I would say, to actually debug. Essentially, you would debug as you would debug any regular program, like using more logging messages and more. No tricks here. There are no. Maybe you will add new GDB flags to avoid, like to don't let interrupt some signals from the Seastar framework. But essentially, no magic here. You need to spend more time debugging before you could.
Okay, I know.
Yeah, the main problem, no stack. Because of the way futures work, no stack.
So do I understand that correctly, that you started to rewrite that code to accommodate more the modern CPUs instead of just rewriting it explicitly to match NVMe and
This is a combination of both. We want to make use of the large core count we have in CPUs in order to exploit these faster storage devices. It plays along for this our goal here.
So for anybody looking to get involved in the Crimson project, where would you suggest they start?
So we have, of course, a basic documentation, and all of our code is open. And I would suggest join our meetings. We have weekly meetings in Tuesday, so you can join and ask about current bugs or missing implementation on things we work at right now. So this is the first step, I would say. And later on is just building in your own and start. We have bugs. We have a tracker with Bug and Trello. Everything is open. So just join us. Just join a meeting, and we'll be happy to if you ping any of us. So.
Anybody else?
I guess that's it. So thank you very much for listening.